Okay, this lesson is lesson 64, and we are going to do talk about a word that we haven't used yet. We're going to introduce you to the idea of something called domain, and then we're going to do some graphing and doing something called inequalities. So I'm going to start on the whiteboard to discuss domain. Okay, this is in the book, so I'm just going to go through it with you. The book talks about, well, in all math, physics, chemistry, and other math, numbers that may be used as replacements for variables are often restricted by the nature of the problem or by a restriction stated in the problem. Let me explain what that means, because that was probably gibberish to you, because it kind of was to me as I heard it coming out of my mouth. Anyway, let's put this in real life. Let's have a real person, let's say, go to the store with 25 cents to buy eggs, okay? This is maybe not that realistic, because I don't know who goes to the store with 25 cents except maybe a 5-year-old who found a quarter in, the couch cushion. But let's say you have 25 cents and your mom sends you to go to the store and buy eggs, and eggs cost 10 cents each, okay? So you have 25 cents, eggs cost 10 cents each. The total amount of money that can be spent on eggs can be represented by this equation, okay? So the total cost is going to be 10 times the number of eggs. Number of eggs. This book likes to use capitals with subscripts. I might have just done 10N. And then cents. So it's 10 times the number of eggs, and that's how much money it'll be in cents. So let's do this as an example. Let's say you go to the store, and because you're 5, I guess you forgot to buy eggs. So you got to the store and you spent 10 cents on 0 eggs. So it costs 0 cents. All right. So let's change it. That's just was 0. So we're saying 0 works. What else works? Can you buy 1 egg? Go to the store, buy 1 egg. The cost is 10 cents times 1 egg. So 1 egg is going to cost 10 cents. That's pretty straightforward. You're probably wondering why we would even use an equation for this. I agree. We're not using an equation to solve this problem. We're using an equation to discuss what domain is. Okay, so let's do 2 eggs. Can we buy 2 eggs? All right. 2 eggs cost 10 times 2, which is 20 cents. Okay? So remember, you have a quarter. You have 25 cents to spend. All right? I'm just going to kind of put that out there. So 2 eggs are possible, and now I know that you know where we're going with this. How about 3 eggs? Okay. Oh, that would be 30 cents. Can't afford it. Okay, so 3 is out of our domain. So let's list what our domain is. We said that we could have 0 eggs. You could buy 1 egg. So here I'm going to write my domain, big D, equals, we'll talk about this in a second. We could get 0 eggs. We could get 1 egg with our 25 cents, and we could get 2 eggs. There is our domain in set notation, 0, 1, or 2. Okay, now the set of permissible, so that's the replacement values that we put in for the variable of this was our variable, or I'll move my camera. That was our variable, and only these 3 numbers were legal to put in there that was in the domain. Okay, so this is how we write domain. You're going to see a big D, and then they're going to list a set. Sometimes the domain, you can have anything replace the variable, and in that case you would write reals. Okay, sometimes the domain will be, and we're going to do this in the next problem in your notes, positive integers. All right, so I was about to ask a question like you guys would be in my class and be able to answer, but positive integers, can someone list me the first 10 positive integers. Okay, the first 10 positive integers are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so with no fractions or decimals. Okay, let's look at our notes now. Okay, let's see if I can get this to focus too, because I'm switching from the whiteboard to notes. And let's see, so go ahead and get your papers ready. They probably already have been. Oh dear, I just broke my pencil. I'm going to do this one in pen. Hopefully do it correctly in pen, because I don't want to make a mistake. Well, I'm going to grab a pencil. Okay, so we have here, we already talked about domain. All right, I told you to read about it. No need to. Unless you are visual, you can go and see what the book has to say about that. Okay, now we're going to graph x is greater than 2 for all real numbers. Okay, so that means we find 2 on our number line. There it is. Now remember, this does not say greater than or equal to. So because of that, it's an open circle. Do you guys remember this from last year? It's an open circle. And now we're talking about all the numbers greater than 2. So if we do that, you're going to graph just like I do. It's going to look like that. Okay, you can do it in different color too if you would like. So we have an open circle here, and you're going to do that, all real numbers. Now, this is going to change on the next one, okay? Because the domain, the possible solution set is only integers, okay? Integers are the actual whole numbers. So let's look at this. X cannot be greater than or equal to 3. What does that mean? Do you guys remember that? If we can change this negative sentence into a positive, that means that, here, I'll write it right here. If x cannot be greater than or equal to 3, that means x is less than 3. Okay, so let's go ahead and find 3. Now, I'm not going to put an open or closed circle because of this integer thing. So what we're talking about is all the integers less than 3. So I'm going to start graphing those. See what I do. Is 2 an integer less than 3? Yep. Is 1. And I remember when I taught algebra last time, mistakes I saw often were when you would graph something like this and forget to look at the domain and end up doing a solid line less than 3. But since it's integers, your solution set is just going to be a bunch of dots, okay? Because in between the dots cannot be part of the solution because it's integers. You can't have partial numbers, half numbers, decimals. Okay, so just remember that. If you have integers as your domain, we're talking about dots on a number line. Okay, the next one is graph x is greater than or equal to -1. And the domain is reals, so that's not dots, that's solid line. So I'm going to find -1, and it's greater than or equal to, so that means I get to do a solid circle because of the part that means or equal to. And x is greater than -1, greater than or equal to -1, so we're going to, again, graph everything up. And so we just solid draw that in. Colored pencils are fun to use here, and pens or whatever. Make sure it doesn't bleed through, but there you go. Example 4. Ooh, now it says positive integers. So I know we're going to deal with dots, and we're looking at all the positive integers less than 1. Well, if it's less than 1, then we're dealing down here, but they want us, the domain is positive integers. So do you see what happened? There are no solutions for these two restrictions for it to be less than -1, but also positive integers are the only ones that can be answers. That's where we finally get to use that idea of an empty set or a null set. So your answer would look like this. We could graph nothing. We'd either write that as a no solution, or you could draw an empty set. Okay, so that was a tricky one. All right, example 5. Again, we've got positive integers, and now it's greater than or equal to -5. Okay, so -5 is down here somewhere. I didn't write it in, but let's say it's way down there. But we got to have x be greater than or equal to -5, but positive integers. So what are the positive integers? They start here and jump. So these, 1 is a positive integer greater than -5, 2 is, 3 is, 4 is, etc. So that's how and we're going to put an arrow there to make sure we know that it's going to go up. Okay, so that is the solution for example 5. All right, this one's a little different. Why? Because x, in all the others above on that paper, x was all by itself. So we knew exactly if x was greater than or bigger, whatever. We had x alone. This one, x isn't isolated yet, so you can't graph it until it is. So what we do is, this is where we use the idea of the additive inverse, that what we did with equations, we can also do with inequalities. Inequality is anytime you have this sign, the greater than sign, all of those. Okay, so just like regular equations, we need to get x by itself. So how do we do that? We subtract 2 from both sides of the inequality. Okay, so if we do that, now we get x is less than -2. Okay, and we go back and look at our domain. It's real, so pretty much anything. We have no restrictions there. So x is less than -2, not or equal to. So that's, I got an open circle there because it cannot equal -2. And it's everything less than -2. So I'm going to have this shaded in down here. All right. So it's a bit of new stuff, knowing that that's allowed, but inequalities behave so much alike with equations, like if this had been an equal sign, that you get to use, there's only one event later on that we'll learn about where it doesn't operate exactly the same. All right, the last example, example 7 in your book, is to graph. Let's see if you can read that. All right, again, we have x is less than, or x minus 3 is greater than or equal to -5, and the domain is integers. So that we have to pay attention to that when we're done with getting x by itself, okay? Plus 3 to both sides. And now we have x is greater than or equal to -5 and a positive 3, -2. X is greater than or equal to -2. And we're dealing with integers. Okay, so it's greater than or equal to -2, not positive integers, just integers. Okay, so if, and it says can be equal to -2. So -2 gets to play, it gets to be a dot. -1 is greater than -2 and is an integer. All of these get to play, and they're all part of the, I put a little arrow there. They're all part of the domain. Okay, so you're gonna want to rush these like on a test or a exercise in the book, and do not lose points because of something as simple as just not looking at what the domain is. Okay, so it looks like you have 4 practice problems.